Ever since the AFC Championship game and into the run-up to the Super Bowl, there's been a lot of talk about deflated footballs. And in particular, to what degree can the pressure of a football go down? To what degree can it get deflated based on temperature differentials from where it was inflated to where it is actually played, especially if it's inflated in a warmer environment, say indoors, and then it's played outdoors in a colder environment. And so to think about this, we'll take out our one of my favorite laws or equations, the ideal gas law. And it tells us that pressure times volume is equal to the number of molecules of our ideal gas we're dealing with. It's measured in terms of moles, but it's just a measure of the number of molecules, times our ideal gas constant, times our temperature. Or if we just want to rearrange it, and I do want to rearrange it because I just want to solve for P here, we can divide both sides by V, and we would be left with P is equal to nRT over V. Now let's think about the exact case of what happened with the New England footballs, or what the argument is for why they might have deflated naturally, why there might not be foul play. The argument is well, maybe they were inflated indoors. They were inflated indoors, where the temperature is just room temperature, so roughly 75 degrees Fahrenheit, which is roughly 24 degrees Celsius. And in order to apply the ideal gas law, we'd want to convert it to Kelvin. So this is approximately 297 Kelvin. That's the indoor temperature. So if we're inflated here, so we're inflated, if we are inflated indoors, inflated over here, and then we play outdoors, and then we play outdoors, where the temperature is roughly 50 degrees Fahrenheit, and that, from what I've read, is actually the temperature on the field during the New England game. 50 degrees Fahrenheit, which is approximately 10 degrees Celsius, which is approximately 283 Kelvin. So the argument being made is, look, you have this temperature drop, and so could that temperature drop, if this temperature drops by a certain percent, could that account for the pressure drop that was actually measured? And the pressure drop that was actually measured was a pressure drop, gauge pressure, and this is an important point because it was glossed over in some of the initial analyses. The gauge pressure indoors, where the ball was inflated, is 12.5, or was 12.5 pounds per square inch. And the gauge pressure outdoors, where the balls felt like they were deflated somehow or had less pressure, was 10.6 pounds per square inch. So to see if these numbers are consistent with each other or consistent with no foul play, let's simplify our ideal gas law a little bit, make it a little bit particular for this circumstance. So in this circumstance, we're going to assume no foul play. If we assume no foul play, that means no air is let into or out of, so the number of molecules aren't going to change. The ideal gas constant obviously shouldn't change. It's a universal gas constant, so this should be constant. And then our volume, let's just assume the football, it's made out of leather, it's relatively rigid. Its volume might have changed a little bit, but for the sake of our analysis, we'll say that it pretty much held up its shape. So its volume stayed constant as we went from indoors to outdoors. So to simplify this equation, let's just call all of this stuff in green. Let's just call that K. If you take your N, multiply it times R, divide it by V, that's just equal to some constant called K. So we can simplify all of this can be simplified to P, pressure, in this case, should be some constant times temperature. Some constant times temperature. Because once again, we're assuming volume doesn't change, we're assuming no air is let in or out. So when you look at it this way, any percent change on temperature should have the same percent change in pressure. So let's see if the change in temperature, the percent change, is consistent with the percent change in pressure that was actually observed. And so when we look at the temperature, we should be doing it in Kelvin. So we should look at this change right over here, going from 297 Kelvin to 283 Kelvin. So what is the drop here? Let's see. It's a drop of 14 Kelvin. Let me get my calculator out. So it's a drop of 14 Kelvin, and we started at 297. So divided by 297. gets us a roughly a, let's just say if we round to the nearest percentage, 0.047, that's roughly a 5% drop. So this right over here is a 5% drop. And I'll write approximately 5% drop. And I'll see what the drop in pressure is. So this is going from 12.5 psi to 10.6 psi. That's 1.9 psi drop. So it's 1.9 psi drop divided by our start, which is 12.5, which looks like a 15.2% drop, or is roughly 15% drop. So this looks like so things are starting to look shady. This looks like a 15% drop. And this is actually what some of the initial analyses, what they did. And they said, oh, look, something clearly shady happened because temperature by itself should only account for a 5% drop in pressure, but there was a 15% drop in pressure. So that would, then, hey, maybe some air was let out somehow. But there was actually a mistake in that initial analysis. Gauge pressure, the 12.5 psi, that's actually not the absolute pressure. What gauge pressure is a measure of, is how much more pressure you have inside than outside. Outside the ball, you do have pressure, standard atmospheric pressure. And it might change depending on the weather, etc. But there is pressure. The pressure is caused by the weight of the atmosphere. So in order to figure out absolute pressure and to figure out the correct percentage change, you need to add the how much more pressure there is inside the ball to what the outside pressure is. And I don't know the exact readings for that day in New England, but the standard pressure is standard atmospheric pressure is 14.7 psi. So plus 14.7 psi gets us to, what is this, 27.2 psi. And if we add the 14.7 over here, once again, to get the true absolute pressure, once again, the gauge reading is just how much pressure inside the football than outside. So if you want the true pressure, the absolute pressure, you add these, and this is going to be 25.2 psi. Now we can calculate the actual percentage drop and compare it to this 5% drop. So let's see. We still have oh, actually, minor mistake. This is 25.3. Don't want to make a little arithmetic error here. 25.3 psi. So we still have the same drop. We have a 1.9 psi drop to go from 27.2 to 25.3, but it's over a larger base, so it should be a lower percentage. And let's calculate what that is. So we have 1.9 psi drop divided by 27.2 psi. 27.2 is equal to, it's a little under a 7% drop. So it looks like approximately a 7% drop. Now, these two things are not exact, but they are a lot closer. And this degree, you're like, okay, there might have been other factors at play. Maybe some of the measurements weren't done exactly right. Maybe actually the ambient pressure was somehow different inside and outside. There's also some possibility that especially when you're outside, if some water, if some precipitation is on the ball, as that precipitation evaporates, it might cool down the ball further, which would drop the pressure even more. So this isn't definitive, but at least the numbers here, when we apply the ideal gas law properly, they pretty much account for most of the pressure drop. So at least here, I wouldn't get too caught up in all of the conspiracy theories.